Part 1. The beginning of the journey. From Earth to the edge of the solar system. Black holes tearing apart massive stars as if they were made of paper. Pulsars spinning at dizzying speeds while unleashing powerful beams of energy that slice through. The cosmos, multicolored nebulae, where newborn stars ignite in spectacular cosmic fireworks. Galaxies of every imaginable color, shape, and size. All of this exists within our universe. Yet here comes something you may never have stopped to consider. The universe is not infinite. It has a boundary, a literal wall, and beyond that wall lies an absolute nothingness, a void so deep it challenges everything we believe we understand. We're about to embark on an extraordinary journey all the way to that cosmic barrier, but before diving into the vast darkness of intergalactic space, we need to grasp something fundamental about the structure of our cosmos. Our universe behaves like a gigantic matryoshka, those Russian nesting dolls stacked one inside another. Open the largest doll and you find a smaller one within. That is a galaxy. Inside it lies an even more delicate doll, our solar system. And the smallest of them all is Earth, our fragile blue home suspended in the immensity of the void. Each of these cosmic dolls has clearly defined edges, and on this journey we will cross every one of them. Before we move deeper into these mysteries, if you enjoy listening to stories about the universe to relax or drift off to sleep, imagine settling in and letting this cosmic narration guide you. Sometimes the best bedtime stories aren't fairy tales at all, but the real enigmas of the endless universe that surrounds us. To carry out this expedition, we need a very unusual spacecraft. No conventional rocket will do. We require something extraordinary, a vessel capable of traveling 100 times faster than the speed of light. Yes, you heard that correctly. Light moves at roughly 300,000 kilometers per second, which means our ship must reach the astonishing speed of 30 million kilometers per second. It's a velocity so extreme it defies the physics we know, but for this hypothetical voyage, it is exactly what we need. Climb aboard, settle into the pilot seat, fasten the harness, and prepare yourself for the most astonishing experience of your life. Power up the main engines. Listen to the deep, thunderous roar vibrating through the ship's frame. Feel the tremor rising through the floor beneath your feet. The moment of departure has arrived. Our first destination lies just 100 kilometers above sea level. It may seem insignificant compared with the cosmic distances we will travel later, but this is our first great boundary. That altitude is roughly 10 times higher than the cruising height of commercial airliners, which typically soar at around 10 to 12 kilometers. This crucial point is known as the Kármán line, named after the Hungarian-American physicist Theodor von Kármán, the first person to mathematically define the boundary between Earth's atmosphere and outer space. The Kármán line separates two entirely distinct worlds. Below it, the atmosphere is dense enough for aircraft to generate aerodynamic lift. Above it, the air becomes so thin that anything crossing this height must move at orbital speed to remain aloft. This invisible line marks where our protective atmosphere ends and true space begins, the vast, silent black ocean stretching outward. Now we accelerate far beyond Earth's orbit. We glide past the moon, that silent companion that has watched the entirety of human history from above. We push onward toward Mars, the red planet that has fascinated us for centuries with its rust-colored deserts and the ghostly traces of ancient riverbeds. We sweep beyond the giant Jupiter, its storms large enough to swallow Earth whole, surrounded by mysterious moons that may hide oceans beneath crusts of ice. We leave behind Saturn, with its radiant rings glittering like jewels in the dark, Uranus with its peculiar tilt that makes it roll sideways around the Sun, and finally Neptune, the distant blue titan marking the dominion of the outer planets. By now we have traveled about 100 astronomical units. 1 AU is the distance between Earth and the Sun, roughly 150 million kilometers. That means we have crossed nearly 15 billion kilometers since departing home. To put this in perspective, if you drove a car at 100 kilometers per hour without stopping, it would take more than 17,000 years to cover this distance. And here we encounter the true edge of our solar system, the heliosphere. This region is one of the most fascinating domains of space. The heliosphere is a protective bubble sculpted by the solar wind, a stream of charged particles continuously flowing outward from the Sun. Imagine the Sun as a colossal garden hose spraying subatomic particles instead of water, creating a bubble that shelters our entire planetary system from dangerous cosmic radiation. At the border of the heliosphere, something remarkable happens. The solar wind slows dramatically. First, it drops from 1,000,000 kilometers per hour to roughly the speed of sound. Then we reach the heliopause, an invisible but very real frontier. Here, the solar wind fades almost completely, and the Sun's influence weakens to nearly nothing. Then our ship encounters what is known as the bow shock. It resembles the V-shaped wave formed at the bow of a ship cutting rapidly through water. At the solar system's edge, we feel the pressure of the interstellar wind, a flow of particles drifting through deep space and colliding against our system's shield. It's like standing at the meeting point of two different oceans, one shaped by our Sun and the other belonging to the vast interstellar expanse. Crossing this unseen but immense barrier, we suddenly enter the absolute darkness of interstellar space. Here, sunlight diminishes until it becomes merely another bright star among thousands. The feeling is overwhelming. We have left behind the only home humanity has ever known. Out here, in this remote and desolate region, lie two objects built by human hands that made this epic crossing before us: Voyager 1 and Voyager 2. Voyager 1 crossed into interstellar space in 2012, becoming the first human-made object to do so, while Voyager 2 followed in 2018, sending invaluable data about this mysterious frontier. These spacecraft are monuments to human curiosity. Launched in 1977, they have been traveling for more than 4 decades, transmitting faint but steady signals back to Earth. They carry the famous golden records, phonograph discs containing sounds and images of Earth, greetings in 55 languages, and music from cultures across the world. They are messages in bottles, drifting through the cosmic ocean, waiting for some distant civilization, perhaps millions of years from now, to discover them. These explorers revealed something extraordinary about the heliosphere. It is not a perfect sphere, as many once assumed. Its shape is more complex, resembling a teardrop or a comet tail. The southern boundary lies about 10 AU closer to the Sun than the northern boundary. This means the heliosphere is being pushed and stretched by the currents of the interstellar medium, distorted asymmetrically like a bubble drifting through a cosmic wind. Now we move deeper into true interstellar space, that immense dark ocean between the stars. Here, the silence is complete. No wind, no sound, only the purest emptiness imaginable. And soon we approach yet another boundary, this time made of ancient rock and ice, surrounding our solar system like a final protective shell. Roughly 2,000 AU beyond our present position lies this structure, the Oort cloud. There it stretches before us, a vast field of cosmic debris. This barrier of stone and ice is breathtaking in scale. It isn't solid, but instead a colossal swarm of billions, perhaps trillions, of comets and icy fragments forming a gigantic spherical shell around the solar system. Scientists believe the Oort cloud is the birthplace of long-period comets that occasionally fall inward, sweeping past the Sun before returning to the frozen depths of space. These icy wanderers carry pristine material from the birth of our solar system, preserved in deep freeze for more than 4.5 billion years. But the objects here are so few and so widely scattered that we drift through them effortlessly. It's like flying through a stadium in which only a handful of grains of sand float in the air. The distances are so vast that close encounters are virtually impossible. Now we are surrounded by complete darkness, wrapped in the black silence of deep interstellar space. Behind us, the Sun has faded into a faint pinpoint, indistinguishable from the other stars scattered across the sky. We have left our home far behind. Ahead of us lie cosmic wonders that surpass imagination. Part 2. Interstellar Space and the Oort Cloud, Crossing the Absolute Darkness. The Milky Way, our home galaxy, stretches roughly 106,000 light-years across. To grasp what that means, remember that a single light-year is the distance light travels in one full year, about 9.46 trillion kilometers. Multiply that by 106,000, and you begin to sense the colossal immensity of our galaxy. In a conventional rocket, even at extreme speeds, the journey across it would require literal billions of years. The timescale is so extreme that by the time you reached the far side, our Sun would already have died, first swelling into a red giant that devours the inner planets, then collapsing into a dim, cooling white dwarf. But you possess something no traditional spacecraft ever had, a vessel capable of bending space-time itself. You accelerate to full power, feeling the engines respond with unimaginable strength. You slip between stars and planets as if racing along a cosmic track. Starlight streaks into glowing lines stretching across your field of vision. Entire solar systems appear and vanish in seconds. Gigantic nebulae, stellar nurseries glowing in impossible hues of electric blue, deep pink, and ghostly green, drift past like clouds of living color. You pass red giants so enormous that, if one replaced our Sun, its surface would extend beyond the orbit of Mars. You glimpse blue supergiants, cosmic titans, shining with such scorching luminosity that our Sun would appear as a faint candle beside them. These massive stars live brief but spectacular lives, burning through their nuclear fuel with furious intensity before erupting as supernovas, capable of lighting up entire galaxies. You witness binary systems where two stars orbit one another in an endless gravitational dance. In some, a dense white dwarf siphons material from its companion, triggering explosive nova events. You pass near a pulsar, the collapsed core of a massive star rotating hundreds of times per second, sweeping beams of radiation from its magnetic poles like a cosmic lighthouse. Its radiation is so intense that approaching too closely would fry every system on your ship in microseconds. You watch open star clusters, groups of young stars born together from a single molecular cloud just a few million years ago. Still close to one another, they shine brightly with the fire of youth. Then you glide past globular clusters, dense spherical swarms containing hundreds of thousands or even millions of ancient stars packed into a tiny region of space. These clusters are among the oldest structures in our galaxy, more than 12 billion years old, nearly as ancient as the universe itself. The diversity of objects you encounter is overwhelming. There are variable stars pulsing in predictable cycles, their brightness rising and falling like cosmic heartbeats. Neutron stars appear, objects so dense that a teaspoon of their matter would weigh as much as an entire mountain on Earth. You pass planetary systems orbiting exotic suns, molten worlds circling so close to their stars that their years last mere hours. Jupiter-sized gas giants drifting alone through interstellar space after violent gravitational interactions ejected them from their original homes. Ocean planets covered entirely in liquid water with not a single patch of land. You cross regions of active star formation where giant molecular clouds collapse under their own gravity. Temperatures here hover just above absolute zero, yet, paradoxically, these frigid realms are where the hottest, brightest stars are born. You see towering pillars of dust and gas, reminiscent of the famous Pillars of Creation in the Eagle Nebula, structures spanning light years, where new solar systems are assembling at this very moment. You encounter supernova remnants, expanding bubbles of hot gas and high-energy particles racing through interstellar space at thousands of kilometers per second. These remnants are cosmic laboratories where heavy elements are forged: the iron in your blood, the calcium in your bones, the gold in your jewelry. All of it was created inside dying stars and scattered across space by cataclysmic explosions. You glide past dark clouds of interstellar dust, blocking the starlight behind them, creating black voids ancient astronomers once called holes in the sky. In reality, these clouds are vast accumulations of dust and molecular gas so dense that visible light cannot penetrate them. Only infrared telescopes can reveal what lies inside: star-forming regions, newborn protostars, and swirling protoplanetary disks where new worlds are slowly taking shape. You witness phenomena of staggering energy: relativistic jets erupting from the poles of forming black holes, accelerating particles nearly to the speed of light. Interstellar shock waves where stellar winds from massive stars crash into surrounding gas, heating it to millions of degrees. Overlapping supernova bubbles created by multiple explosions over millions of years in the same region. The Milky Way is far more than a random scattering of stars. It has structure, a thin disk where most young stars reside, glowing spiral arms sweeping outward from a bright central bulge filled with old stars, a vast spherical halo extending far beyond the visible disk, containing ancient globular clusters, and the invisible dark matter whose gravity binds the galaxy together. You pierce one of the spiral arms, majestic ribbons of reinforced density moving through the galactic disk. These arms aren't fixed structures of stars, they are waves of density compressing gas and triggering bursts of star formation. That is why the spiral arms shine so brightly. Within them, young, hot, luminous stars burn with blinding intensity. Within minutes, something that should take hundreds of thousands of years, you reach the edge of our galaxy. The transition is sudden. Star density drops drastically. The stars you see now are much farther apart, mostly old, low-mass stars drifting through the galactic halo. The combined glow of the Milky Way's hundreds of billions of stars now lies behind you, stretched into a misty band of distant light. The interstellar wind disappears. Out here, the space beyond the galaxy is even emptier than interstellar space inside it. Matter density drops to nearly 1 atom per cubic meter, compared with several atoms per cubic centimeter within the disk. Everything around you becomes scattered points of light. They aren't stars. At these distances, your eyes can no longer resolve individual stars. Each shining mark is an entire galaxy, each containing hundreds of billions of stars, countless solar systems, and possibly trillions of planets. Every point of light represents an island universe on a scale rivaling or exceeding the Milky Way. Some galaxies are elegant spirals like ours, their arms curling gracefully from a radiant core. Others are smooth, quiet ellipticals filled with ancient reddish stars. Still others are irregular, chaotic shapes born from cosmic collisions and mergers. You even see dwarf galaxies, small systems containing only a few billion stars, orbiting larger galaxies like satellites. Now you consult a map, a cosmic map, tracing a route to the boundary of the observable universe. It is a masterpiece of decades of telescope observations and redshift measurements of millions of galaxies, showing the three-dimensional structure of the cosmos on its largest scales. Here you are, near the Milky Way. Our galaxy belongs to a cluster called the Local Group, home to about 80 known galaxies. The dominant members are the Milky Way and Andromeda, our nearest galactic neighbor, about 2.5 million light-years away. Andromeda is slightly larger, perhaps containing 1 trillion stars, compared with our 200 to 400 billion. Together with the Triangulum galaxy, M33, and dozens of dwarf galaxies, they form our immediate cosmic neighborhood. But the Local Group is only the beginning. It belongs to a much larger structure, the Virgo supercluster, which contains at least 100 galaxy groups and clusters, including the Virgo cluster itself, with more than 2,000 galaxies. Even this giant supercluster is only part of something far greater. Recent studies reveal that we belong to Laniakea, a gigantic supercluster of superclusters containing roughly 100,000 galaxies spread across 520 million light-years. Its name, from Hawaiian, means immense heaven. Yet even Laniakea is just a tiny street in an unimaginable cosmic metropolis. Zoom out further and you see the Hydra Centaurus supercluster, another colossal structure holding thousands of galaxies. They appear as dots on the map, but each dot is an entire galaxy overflowing with wonders. Zoom out fully, and at last you see the whole picture, the entire observable universe. The view is awe-inspiring. The observable cosmos has a radius of about 46.5 billion light-years and contains at least 2 trillion galaxies, each filled with hundreds of billions of stars. The scale is so vast that the human mind cannot truly comprehend it. For a long time we believed the universe was infinite, but now we may have evidence that it has a boundary. And that boundary seems to lie roughly 10 billion light-years from home, in a region known as the Eridanus supervoid. Part 3. The Eridanus supervoid. Evidence of collisions between universes. Even if you could travel at the speed of light, the journey to the Eridanus supervoid would take around 10 billion years. To place this in a truly staggering perspective, that span is roughly twice the entire age of planet Earth. Our world formed about 4.5 billion years ago from a rotating disk of dust and gas around the young sun. During that immense stretch of time, life evolved from simple, single-celled organisms into the complex biosphere we see today. Continents formed, drifted apart, and collided again. Oceans appeared, shifted, and transformed. 5 major mass extinctions wiped out most life on Earth, only for life to recover each time and explode into new forms. During a journey as long as the one required to reach the Eridanus supervoid, our sun would undergo dramatic and irreversible changes. Stars like our sun live for roughly 10 billion years. At about 4.6 billion years old, the sun is halfway through its life. But in another 5 billion years, it will exhaust all the hydrogen in its core and begin fusing helium, an enormously more energetic and violent process. When this begins, the sun will expand dramatically, becoming what astronomers call a red giant. Its glowing surface will reach beyond Mercury's orbit, possibly even beyond Venus, and may stretch all the way to Earth. Temperatures on our planet would soar to hellish extremes. Oceans would boil and vanish entirely. The atmosphere would be stripped away by the sun's blistering radiation. Earth's surface would melt into oceans of magma. All traces of life, every building, every artifact of our civilization would be incinerated and erased forever. After several 100 million years in its red giant phase, the sun will no longer have the mass required to fuse heavier elements. It won't go supernova. Only far more massive stars do that. Instead, the sun will cast off its outer layers in a beautiful planetary nebula, leaving behind a dense, scorching core roughly the size of Earth, but containing about half the mass of the present sun. This remnant is called a white dwarf, and it will cool over trillions of years until it eventually becomes a cold, dark, black dwarf. So if you truly embarked on this 10 billion year journey at light speed and then attempted to return home, another 10 billion years, by the time you arrived back, our solar system would no longer exist. The sun would have faded or expanded and collapsed long ago, destroying the inner planets. Mercury, Venus, Earth, and possibly even Mars would be gone, either consumed or vaporized. The outer planets, like Jupiter and Saturn, might survive, but they would orbit a small, dim white dwarf rather than the brilliant yellow star we know. And there's more. If you somehow survived such an incomprehensibly long journey and returned home, you would discover that the Milky Way itself no longer existed in its familiar form. Why? Because by then it would have collided with the Andromeda Galaxy and merged into an entirely new cosmic structure. This galactic collision isn't speculative. It is a guaranteed event. Astronomers have measured Andromeda's motion with precision and found that it is approaching us at about 110 kilometers per second, nearly 400,000 kilometers per hour. In cosmic terms, the Milky Way and Andromeda are headed straight toward each other. The first stages of this collision will begin in roughly 4.5 billion years. Interestingly, at the same time the Sun begins its red giant transformation. The merging process will not be instantaneous. It will take billions of years for the galaxies to pass through each other, separate, collide again, and eventually fuse into one enormous elliptical galaxy that astronomers have already nicknamed Milkomeda. Contrary to what you might imagine, this collision won't involve stars smashing together like cosmic billiard balls. The distances between stars are so immense that the probability of direct collisions is effectively zero. Instead, the stars of both galaxies will simply pass through one another, like two swarms of bees intermingling, without the bees themselves crashing together. But the gravitational interaction will be dramatic. Spiral arms will twist and tear apart. Long streams of stars will be ripped from both galaxies and flung into intergalactic space. Massive clouds of interstellar gas will collide at incredible speeds, compressing and triggering explosive bursts of star formation. Millions of new stars, igniting in a relatively short cosmic moment. The night sky on any surviving planet would be breathtaking, filled with glowing star-forming regions and brilliant nebulae. If our solar system still exists in some form by then, it will likely be thrown into a completely different orbit around the center of the newly merged galaxy. We might end up much closer to the galactic core, or be pushed outward into the halo. In the worst case, the solar system could be ejected entirely, doomed to drift alone through intergalactic space forever. Fortunately, your ship bends space-time itself, allowing a journey that would normally span 20 billion years to last only a few subjective seconds. This hypothetical technology creates what physicists call a warp bubble, or Alcubierre drive. named after Mexican physicist Miguel Alcubierre, who proposed the idea in 1994. The concept is extraordinary. Instead of the ship moving through space, space itself contracts in front of the ship and expands behind it, forming a wave in the fabric of space-time that carries the vessel forward. Inside the bubble, the ship does not technically exceed the speed of light relative to its immediate surroundings, yet it can cross vast distances in very short periods, because space-time itself is being manipulated. It's a kind of loophole in the laws of physics. Excellent. You have finally arrived at your destination, the Eridanus supervoid, also known as the cold spot. Some scientists consider this region the strongest evidence that our universe once collided with something massive enough to leave a vast scar in the fabric of reality. The Eridanus supervoid is an empty, frigid expanse roughly 1 billion light-years wide. To visualize this scale, imagine an enormous bowl capable of holding at least 10,000 galaxies the size of the Milky Way, each with hundreds of billions of stars, planets, nebulae, and cosmic phenomena. And yet this region is almost completely empty. It is a void within a void, a place where matter is dramatically less dense than expected under standard cosmological models. This supervoid appears to have been created by a cosmic accident of unimaginable proportions, an event so massive and violent that it pushes against our understanding of what is possible. What kind of event could carve out such a colossal emptiness? The most fascinating and controversial theory proposes that the object that smashed into our universe was an entire other universe. Yes, you read that correctly, another universe. The idea may sound like extreme science fiction, yet it has serious theoretical foundations in some of the most advanced branches of modern physics. Other universes may exist, and in some models, they must exist. Imagine that everything in our observable universe, its trillions of galaxies, all matter and energy, all space and time, is contained within a single enormous bubble. That bubble does not float in any ordinary space, but within a higher dimensional structure physicists call the multiverse. And here comes the truly mind-bending part. There may be an infinite number of such bubbles, each representing a separate universe with its own physical laws, fundamental constants, and possibly even different numbers of spatial dimensions. These bubble universes may have formed during the event we call the Big Bang. More precisely, during the period of cosmic inflation that occurred within the first fractions of a second. Cosmic inflation, proposed primarily by physicist Alan Guth in 1980, suggests that the universe underwent an exponentially rapid expansion between 10 to the minus 36 and 10 to the minus 32 seconds after its birth. During this unimaginably brief interval, the universe expanded from something smaller than an atom to the size of a tennis ball, or larger. This expansion was so abrupt that different regions lost causal contact with one another, becoming isolated in their own self-contained bubbles of space-time. These universes may be completely different from ours. They could contain galaxies and nebulae fashioned from exotic forms of matter that do not exist here. They might have 4, 5, or even 11 spatial dimensions, as suggested in some versions of string theory. The fundamental constants of physics could also be different. In our universe, the speed of light is fixed at 299,792,458 meters per second. The electron has a precise charge. Gravity behaves according to a specific constant, and so on. But in another universe, these constants could vary dramatically. Gravity might be far stronger or weaker. The nuclear forces binding atoms could differ enormously. The speed of light might be something entirely different. These shifts would lead to drastic consequences. In some universes, gravity might be so strong that everything collapses immediately into giant black holes. In others, gravity might be so weak that stars and galaxies never form. Some universes might contain only pure energy, with no matter at all. Others could possess unfamiliar fundamental particles, unlike anything we encounter. And these bubble universes may also represent parallel realms in a far more literal sense. This leads to the idea of parallel worlds, the many worlds interpretation of quantum mechanics, proposed by Hugh Everett III in 1957. According to this interpretation, every quantum event with multiple possible outcomes causes the universe to split, creating a separate reality for each outcome. This means that if you choose cereal today instead of oatmeal, there exists another universe where your identical counterpart chose the oatmeal. If you walked one route to work, another version of you in another universe took the other route. Every decision, every choice, every quantum fluctuation spawns new universes in which different outcomes unfolded. The implications are immense and unsettling. There are versions of you who made every possible decision. Versions where you were never born. Versions where humanity never evolved because the asteroid that killed the dinosaurs never struck Earth. Versions where Einstein never developed relativity. Where major historical events unfolded differently. Where life never emerged at all. And because the number of decisions and quantum events is effectively infinite, the number of parallel universes is also infinite, an endless cosmos filled with endlessly branching variations of reality. The human mind cannot fully process what this truly means. Part 4. Black holes as portals, the posics of traveling between universes. Just like an ordinary soap bubble drifting lazily through the air, our universe has a wall, a physical boundary that marks where our reality ends and where something else begins, whatever that something may ultimately be. That invisible, yet very real frontier lies near the Eridanus supervoid, that enormous, empty region we have just explored. Long ago, billions upon billions of years in the cosmic past, another universe bubble passed close to ours as both drifted silently through the multiverse. As these two cosmic bubbles drew nearer, something truly extraordinary began to happen. Their gravitational fields, which extend well beyond the visible edges of each universe, started to interact and tug on one another. Think of how two magnets affect each other, even before they touch. You can feel the pull or push as you bring them closer together in your hands. In a similar way, these two universes began to sense one another through gravity, that fundamental force that permeates all of space-time and shapes the motion of everything from falling apples to spinning galaxies. Our boundary wall began to deform under the gravitational influence of the neighboring universe. The very fabric of space-time started to stretch and bow toward the other cosmos, as if it were an elastic sheet being tugged from one side by an invisible hand. Picture a flexible rubber membrane. Press on it from one direction, and it curves, warps, and sags toward the point of pressure. That is exactly what was happening to the edge of our universe, but on an inconceivably larger scale. The same thing was happening on the other side. The neighboring universe also felt this distortion, its own boundary wall being pulled toward us by the mutual gravitational attraction. The two walls curved toward each other, like two people leaning in for a kiss, drawing inexorably closer across the emptiness of the multiverse, until the gap between them shrank to almost nothing. Then, at some point about 13 billion years ago, shortly after the Big Bang, when the universe was still young, dense, and blazing hot, the walls of our universes finally came into physical contact. It was a moment of almost unimaginable cosmic importance. Two completely separate realities, each with its own history, its own possible physical laws, its own space-time structure, touching for the very first time and briefly sharing a common boundary. What happened at that instant of contact? Theoretical physicists have been speculating about this for years, sketching equations and scenarios on blackboards filled with symbols. At the exact point where the membranes touched, the physical laws of both universes would have come into direct conflict. The fundamental constants of each universe, the forces governing matter and energy, everything, would have struggled to assert dominance over the same tiny region of spacetime. The result would be a chaotic transition zone where reality itself became unstable and turbulent, a storm at the border between worlds. But universe bubbles are not static objects pinned in place. They are constantly moving through the multiverse, driven by the ongoing expansion of spacetime and the deep currents running through the underlying fabric of reality. As the bubbles continued to drift, their temporary connection began to stretch and thin. The point of contact elongated, becoming a narrow, fragile thread, like the thin neck of water that forms when two droplets briefly merge and then begin to pull apart again, clinging together for a moment longer than they should. Tension at the connection point rose dramatically. The fabric of space-time was stretched to its limit, strained like an overworked muscle. Finally, like an overstressed rubber band, the connection snapped violently. The two universe bubbles recoiled and separated, once again becoming independent, isolated realms, with no direct contact between them. But this parting was neither clean nor gentle, and it left permanent damage behind. When the connection broke, the other universe literally tore a huge chunk out of ours. Think of peeling a sticker off a surface. Sometimes it pulls away small fragments of the underlying material, leaving behind a rough, scarred patch. Something similar happened here, only on a scale beyond comprehension. Entire galaxies, massive clumps of matter, enormous volumes of space-time itself were ripped from our universe and absorbed into the neighboring one as it moved away. At the exact site of that cataclysmic collision and separation, a vast cold void was left behind. All the matter that once existed there, all the galaxies that should have filled that region of space, simply vanished, carried off into the other universe. What remained was the Eridanus supervoid, a permanent cosmic scar marking the place where our universe was wounded by contact with another reality, a bruise on the skin of the cosmos that has never fully faded. This supervoid is remarkable not only for how empty it is, but also for its temperature. Measurements of the cosmic microwave background, the relic radiation from the Big Bang that fills all of space like a faint radio hiss, show that this region is about 70 microkelvins colder than the surrounding areas. That may not sound like much at first glance, but in cosmology, it is an enormous temperature difference, a glaring anomaly in what should be a nearly uniform cosmic background, one that demands an extraordinary explanation rather than a simple coincidence. The fundamental problem with detecting and studying the boundaries of the universe is that the cosmos looks essentially the same to every observer, no matter where they are or which way they look. This is a core idea in cosmology, known as the cosmological principle, which states that on sufficiently large scales, the universe is homogeneous and isotropic. It looks the same in all directions and from all locations, with no privileged center or special vantage point. To get a better feel for this difficulty, consider a simple but powerful analogy. Imagine a perfectly inflated basketball hanging in midair. Now place an ant on the surface of that ball and ask it to find the edge of its spherical world. What happens? The ant will start walking around the ball, tracing endless loops over its curved surface, circling again and again. It could walk in circles forever, covering kilometers and kilometers from its tiny point of view. Yet the landscape around it would never change in any meaningful way. All it would ever see is a gently curving horizon extending in every direction. From its two-dimensional perspective, confined to the surface of the sphere, the ant would have no way to detect that it is walking on a closed, curved object. Its world would feel flat and infinite, with no obvious boundary or edge to discover. This occurs because the basketball looks exactly the same from every point on its surface. There are no natural markers, no built-in signs that say, "This is the North Pole," or "This is the equator," unless we paint them on artificially with ink or dye. Every point is fundamentally equivalent to every other point from the ant's limited perspective. The same thing happens to us when we try to find the edge of our universe. No matter which direction we point our most powerful telescopes, we see roughly the same distribution of galaxies, the same large-scale structure, the same kinds of cosmic objects. There is no giant sign in the sky declaring, "The boundary of the universe lies this way." The universe does not offer us convenient arrows or labels. All of this stems from the way we imagine and perceive reality in three spatial dimensions, and from the limits of the human brain's ability to process spatial information. We evolved to navigate a three-dimensional environment, left and right, forward and backward, up and down, and our intuition is strongly rooted in that everyday experience. Our minds are simply not built to intuitively picture higher dimensions, even though the mathematics describing them is perfectly consistent. Take a simple square. It is a perfectly ordinary two-dimensional figure with 4 equal sides and 4 right angles. Anyone can sketch and understand a square. But if you add depth, a third dimension, and shift your viewpoint, voila, the square becomes a cube. The cube is just the three-dimensional version of the square, yet for a being confined to a flat two-dimensional world, like a cartoon character trapped on a sheet of paper, a cube would be impossible to visualize or fully comprehend in its entirety. Now take one more step. A cube in three-dimensional space has 6 square faces, 12 edges, and 8 vertices. But if we could see that same object in a 4-dimensional space, we would discover that it is merely one face of a hypercube, or tesseract, a 4-dimensional object with 8 cubic faces, 24 square faces, 32 edges, and 16 vertices. For us, locked into three-dimensional perception, the full hypercube can never be truly seen, only described mathematically and represented by distorted three-dimensional projections that hint at its true form. If we could perceive the universe in 4 full spatial dimensions, in addition to time, the square we currently see might be something far richer and more intricate. The observable universe could be just a three-dimensional projection, a shadow cast by a much more elaborate structure existing in higher dimensions we cannot directly sense. This limitation in our spatial perception makes finding the true boundary of the universe extraordinarily difficult, perhaps impossible, using conventional observational methods. It is like asking that ant on the basketball to determine the complete shape of the object it walks on. From its two-dimensional point of view, the task is essentially hopeless. Yet perhaps, just perhaps, we might one day step outside our home universe bubble and visit those other parallel or alternate universes. The key to such a journey could lie hidden inside one of the most mysterious, extreme, and fascinating objects in existence, a black hole. A black hole is truly one of the most extraordinary phenomena nature can create. These objects are so incredibly dense and massive that they do more than curve the space around them. They also warfare time itself in dramatic ways. Black hole physics sits at the crossroads of Einstein's general relativity and gravitational extremes that simply do not occur anywhere else in the cosmos. To picture how a black hole warps space-time, imagine a perfectly stretched horizontal trampoline. That taut, flat surface represents ordinary space-time. Now place a heavy rock in the center. The fabric sags, forming a deep depression. The closer you get to the rock, the steeper the curvature becomes. This is essentially how gravity works in Einstein's view. Massive objects bend the fabric of space-time, and other objects move along those curves as if sliding down invisible slopes. But a black hole takes this to an unimaginable extreme. It is as though you dropped an infinitely dense rock onto the trampoline, so heavy that it punches a bottomless pit straight through the fabric. The curvature becomes so steep that at a certain point, called the event horizon, not even light can escape. Once you cross that invisible threshold, you are doomed to fall inward, toward the singularity, a point of effectively infinite density where our known laws of physics break down completely and our equations cease to make sense. The gravitational effects near a black hole are so intense that time behaves in bizarre, counterintuitive ways. If you watched someone falling toward a black hole from a safe distance, you would see something strange. As they neared the event horizon, their motion would appear to slow more and more. They would move as though trapped in extreme slow motion. Right at the horizon, from your external point of view, they would seem frozen in time, their image fading away as the light from their body redshifts and grows dimmer and dimmer. Yet from the falling person's perspective, nothing special happens at the event horizon, at least in the case of a supermassive black hole large enough that tidal forces are initially gentle. For them, time would feel perfectly normal. They would simply keep falling toward the center, unable to escape, not even at the speed of light. This mismatch between perspectives, this strange disagreement about the flow of time, is one of the most intriguing and mind-bending features of general relativity. Once you are trapped within a black hole's gravitational grip, past the event horizon, there is no way out. Gravity is simply too strong. Even with a rocket of infinite thrust, you could not fight your way free. Space-time itself is so sharply curved that every path, every possible trajectory leads inward toward the center and finally to the singularity, like water funneling down a cosmic drain. We still do not truly know what lies at the heart of a black hole, inside that singularity where density becomes theoretically infinite and space-time's curvature diverges without limit. Our equations explode into infinities at that point, a strong hint that our theories are incomplete under such conditions. We need a fully unified theory of quantum gravity to understand what actually happens there, a framework that marries general relativity with quantum mechanics, but we do not yet have one. Some scientists and theoretical physicists speculate that white holes might also exist. In theory, these objects would be born alongside black holes as their mathematical counterparts, emerging naturally from certain exact solutions of Einstein's equations. Aside from the descriptive color in their names, they are the exact opposites of black holes in every way. Where a black hole swallows everything that crosses its event horizon and lets nothing escape, a white hole would do the opposite. It would continuously spew out matter and energy, while nothing could get close enough to fall in. It would behave like a time-reversed black hole, a source rather than a sink, a cosmic fountain instead of a cosmic drain. At the moment, we have no direct observational evidence for such objects. No telescope has ever unambiguously detected a white hole in the universe. Yet when Einstein's general relativity is explored rigorously and mathematically, it suggests that white holes should at least be possible in principle, strange mirror images of black holes, hiding somewhere in the grand equations of space-time. Part 5. Wormholes and gigantic cosmic structures, the walls of the universe. This is where the theory becomes truly fascinating and wildly speculative. Some scientists suggest that black holes and white holes might be connected through what is known as an Einstein-Rosen bridge, more commonly called a wormhole. This idea was first worked out in 1935 by Albert Einstein and his colleague Nathan Rosen, although at the time it existed purely as a theoretical, mathematical construct, written in chalk on blackboards rather than in the machinery of real spacecraft. A wormhole would essentially be a tunnel or shortcut through space-time that links two distant points in the universe, or possibly even two completely different universes. Imagine taking a sheet of paper and marking two dots at opposite edges, point A and point B. Normally, to go from A to B, you would need to travel along the surface of the paper, following the long, flat route from one side to the other. But now, fold the paper so that point A lies directly above point B, almost touching it. If you could punch a tiny hole straight through both points, you would suddenly have an instant shortcut between them. That is essentially what a wormhole would be in real space-time. Instead of traveling thousands or millions of light years through ordinary space, you would simply enter one end of the wormhole, the black hole mouth, and exit through the other end, the white hole mouth, appearing almost instantly in a completely different region of the universe, or perhaps in some parallel universe whose stars and galaxies have never been seen from our own. In science fiction stories, starships slip through such tunnels as casually as cars take a highway on-ramp. But here the idea emerges from sober, rigorous equations rather than from arbitrary fantasy. Some theoretical physicists suspect that such shortcuts through space-time might exist inside certain special kinds of black holes. Not every black hole would necessarily contain a traversable wormhole. Most would almost certainly lead straight to destructive singularities. But perhaps, under the right conditions and with the right configuration of matter and energy, a black hole could shelter a stable tunnel that would allow you to pass through and emerge somewhere else, like a door half hidden in the dark fabric of the cosmos. The main problem with this enchanting idea is brutally practical. How do you survive the act of falling into a black hole in the first place? This is one of the greatest obstacles for any serious proposal of interstellar or interuniversal travel involving black holes. The answer, interestingly enough, has to do with the size and mass of the black hole you choose. You simply have to pick a black hole that is large enough, specifically a supermassive black hole of the kind found in the centers of galaxies. The crucial difference is a matter of gravitational gradient, how quickly the strength of gravity changes over distance. Imagine falling toward a stellar mass black hole, one formed from the collapse of a massive star. These black holes typically have between 5 and 100 times the Sun's mass, and their event horizons are relatively small, perhaps only 30 to 300 kilometers across. If you approached one of these head first, the gravity acting on your head would be much stronger than the gravity acting on your feet, simply because your head is a couple of meters closer to the center than your feet. This difference in gravitational pull along your body produces what physicists call tidal forces. These forces would stretch you vertically while squeezing you horizontally. The effect is similar to pulling on a piece of modeling clay. It lengthens in one direction and thins in the others. In the case of a stellar black hole, those tidal forces would be absolutely catastrophic. As you neared the event horizon of a small black hole, the tidal forces would grow so intense that they would literally tear you apart, molecule by molecule, in a process astrophysicists have nicknamed, somewhat darkly, spaghettification. Your body would be drawn out into a long, thin filament, like a strand of cosmic spaghetti. First your bones would snap, then your tissues would rip, then your cells would separate, and eventually even your atoms would be pulled apart. It would be a gruesome death, and it would certainly not allow you to explore whatever lies inside a black hole. Choose a supermassive black hole, however, and the situation changes dramatically. These cosmic behemoths, found in the centers of nearly all large galaxies, can contain millions or even billions of solar masses. The supermassive black hole at the heart of our Milky Way, called Sagittarius A star, has a mass of about 4 million suns. Some of the largest known supermassive black holes tip the scales at more than 40 billion solar masses. Because these black holes are so incredibly massive, their event horizons are correspondingly enormous. The event horizon of Sagittarius A star spans roughly 44 million kilometers, comparable to the size of Mercury's orbit around the Sun. The biggest supermassive black holes have horizons that stretch across billions of kilometers, dwarfing entire planetary systems and turning the surrounding regions into maelstroms of swirling plasma and distorted starlight. The key point is that although these black holes are much more massive, their gravity increases more gently as you approach them, because the event horizon is so far from the central singularity. In mathematical terms, the gravitational force decreases with the square of the distance from the center, while the gradient of that force, how rapidly it changes, falls off with the cube of the distance. That means that at the event horizon of a supermassive black hole, the difference in gravitational pull between your head and your feet would be relatively small, perhaps almost negligible. You could cross the horizon without experiencing lethal tidal forces. In fact, according to detailed calculations, you might not notice anything especially dramatic as you pass that point of no return, even though there would be no way back for you ever again. The gravity at your head and at your feet would be nearly the same, keeping you roughly intact and surprisingly comfortable, at least at first. You could survive the crossing of the event horizon and venture into the interior of the black hole for a while. Eventually, however, as you drew closer to the central singularity, tidal forces would rise again to destructive levels, and your fate would be sealed. But there would be a period of time before that final moment arrives, a brief window during which you could witness physical phenomena impossible to reproduce in any human laboratory. Who knows, perhaps if you managed a carefully controlled descent into such a colossal black hole, you might find yourself in a universe completely different from our own, a place where different physical laws hold sway, where the fundamental constants take on unfamiliar values, where the very fabric of space-time is woven in another pattern. You might emerge from a corresponding white hole in that other universe, being flung outward into a strange cosmos that defies every expectation and every familiar map of the stars. For now, though, all of this remains speculative theory, elegant equations and bold ideas in advanced theoretical physics, but without experimental confirmation. No one has ever fallen into a black hole and lived to describe the journey, and we have no practical way to test these concepts directly with present-day technology. Even so, the mathematics suggests that such things are at least possible, and in science, possibilities written into the equations have a persistent habit of showing up somewhere in the universe. Let us now change gears and talk about some of the largest and most spectacular structures known in our observable universe. These are the true walls of the cosmos, structures so vast that even galaxy superclusters look almost modest when set beside them. One of these monumental formations is the South Pole Wall. This is an immense wall of galaxies, stretching across a significant portion of the southern sky. To reach it, our spaceship, traveling at 100 times the speed of light, would still need around 63,000 years to cover the distance. Pause on that number for a moment. Even with a ship that can fly 100 times faster than light, which already races through space at 300,000 kilometers per second, the trip would last a full 63 millennia. That is longer than all of human civilization has existed. The first cities arose only about 10,000 years ago. Agriculture began a mere 12,000 years ago. All of recorded human history fits into roughly the last 5,000 years. A 63,000-year journey is simply beyond human intuition. At one point, you might be tempted to say that the trip to the South Pole Wall would take longer than the entire age of our solar system, which formed about 4.6 billion years ago. Wait, that does not add up at all. Recheck the numbers and you quickly see that 63,000 years is utterly negligible compared with billions of years. Yet the underlying message remains. On human timescales, these cosmic distances are so great that they push our intuition to its breaking point and remind us just how tiny and parochial our everyday scale truly is. Even on cosmic scales, where distances are usually measured in millions or billions of light years, this wall is enormous. The South Pole Wall spans roughly 1.37 billion light years from end to end. That number is so enormous that it is almost impossible to visualize in any meaningful way. To get a better feeling for its truly epic size, remember that the Milky Way, our home galaxy with its 200 to 400 billion stars spread across vast tracts of space, is only about 100,000 light-years wide. The South Pole Wall is roughly 13,700 times longer than the diameter of the entire Milky Way. If the Milky Way were the size of a tiny coin in your hand, this structure would be like a highway stretching clear across an entire continent, from one horizon to the other. This wall contains tens of thousands of galaxies, each comparable in size to the Milky Way, all arranged in a long filamentary structure that extends through a massive swath of the observable universe. It is like a gigantic cosmic curtain woven out of galaxies, hanging in the darkness of intergalactic space. And here comes the truly maddening part for astronomers. You cannot simply point a telescope and see this wall directly, even with the most powerful instruments currently in existence. Why not? Because the Milky Way itself blocks our view. Our own galaxy lies in the way, obscuring our sightline to this enormous structure. It is like trying to admire the night sky from the center of a city blazing with lights, somewhere like Las Vegas or Times Square in New York. The city's light pollution is so intense and overwhelming that it drowns out the faint glow of distant stars. You see only the brightest points of light and lose most of the subtle beauty of the sky. In the same way, the Milky Way, being our home galaxy and surrounding us on all sides, shines so brightly in our instruments that it hides more distant objects that happen to lie behind it. This problem is especially severe when we look toward the plane of the galactic disk, where most of the Milky Way's stars are concentrated. That zone is known as the zone of avoidance, a band of the sky where our ability to observe distant galaxies is severely limited by interstellar dust, gas, and the sheer number of stars in our own galaxy. So how did scientists manage to detect the South Pole Wall and other similar structures if they cannot see them clearly in visible light? They did it by measuring something called the redshift of galaxies. Redshift is a foundational concept in observational cosmology, and it deserves a careful look and a bit of patient imagination. We know that every large-scale object in the universe is moving, and not in some random, chaotic way. On average, galaxies are all receding from one another. This is a direct consequence of the Big Bang, which occurred about 13.8 billion years ago. The universe itself is expanding, and as a result, The space between galaxies is continually growing. It is not that galaxies are flying through a static background. Rather, space itself is stretching, carrying galaxies along like raisins embedded in rising dough. When a galaxy moves away from us because of this expansion, something interesting happens to the light it emits. The light waves get stretched along with space, a relativistic version of the Doppler effect. This stretching shifts the light toward longer wavelengths. In the visible spectrum, longer wavelengths correspond to the red end, hence the term redshift. The faster a galaxy is receding from us, the stronger its redshift. And according to Hubble's law, discovered by Edwin Hubble in 1929, the speed at which a galaxy moves away is proportional to its distance. The more distant the galaxy, the faster it recedes. Therefore, by measuring a galaxy's redshift, astronomers can estimate its distance from us with impressive accuracy, turning spectral lines into precise cosmic yardsticks. By measuring the redshifts of millions of galaxies across the sky, astronomers can construct three-dimensional maps of the universe that show how galaxies are arranged in space. These maps reveal that galaxies are not scattered randomly like grains of sand tossed in the wind, but instead form an intricate structure of filaments, walls, and vast, empty voids, a pattern often likened to a sponge, a foam, or a cosmic web, stretching across the observable universe, a gigantic lattice in which each knot is a cluster of galaxies and each gap is a chasm almost empty of matter. Part 6. The Hercules Corona Borealis Great Wall and Quasars, Beacons of the Priminate Universe. And that wall we have just explored, the South Pole Wall, is not even the largest structure known in our observable universe. There is something even more colossal, something so vast that it challenges our standard cosmological models and forces us to rethink what we believed we knew about how the universe formed and evolved over billions of years. This is the Hercules Corona Borealis Great Wall, named because it lies in the direction of the constellations Hercules and Corona Borealis as seen from Earth. It is a gigantic, roughly flat superstructure about 10 billion light-years across. To put that staggering number into any kind of perspective, it represents around 10% of the entire diameter of the observable universe. Remember that the observable universe has a diameter of about 93 billion light-years. That figure is not the age of the universe, 13.8 billion years, because space itself has been expanding all that time, carrying galaxies far beyond the distance light could have covered on a straight-line journey. The Hercules Corona Borealis Great Wall stretches over 10 billion light-years, a substantial fraction of that total distance, like a titanic scar etched into the cosmic web. This presents serious theoretical problems for cosmologists. According to the cosmological principle, the universe should be approximately homogeneous on sufficiently large scales. There should not be structures so enormous that they occupy a significant fraction of the observable universe. And yet here this massive structure stands, blatantly defying those expectations and demanding an explanation. For such a large structure to form, the galaxies that compose it would need time to clump together under the pull of gravity. But when we calculate how long it should take to assemble something of this size, we find that the universe simply has not existed long enough, according to our current models. It is like discovering a 100-story skyscraper in a city that has existed for only a single year. Something clearly does not match our understanding of how things are built. This Great Wall is indeed a cosmic wall, but not in the sense of a solid, impenetrable barrier. Rather, it is an extremely dense aggregation of galaxies, a gigantic conglomeration of matter organized into a massive filamentary sheet. Picture thousands upon thousands of galaxies, each containing hundreds of billions of stars, all gathered relatively close together in cosmic terms, forming a page or wall of galaxies stretched across a vast region of space. We were able to detect this gigantic structure in a fascinating and indirect way by observing gamma-ray bursts. Gamma-ray bursts, or GRBs, are literally the brightest and most energetic electromagnetic events that occur in the universe. These explosions are so powerful that for a few brief seconds they can outshine all the other stars in the observable universe combined. Such bursts occur when massive stars collapse at the ends of their lives, forming black holes, or when two ultra-dense objects, like neutron stars, collide and merge. The energy released is so colossally huge that it can be detected across truly cosmic distances. Even if a gamma-ray burst erupted right at the far edge of the observable universe, nearly 13.8 billion light-years away, our specialized space telescopes could still pick up its signal. This extreme detectability makes GRBs invaluable tools for mapping the distant universe. They are like brilliant beacons that let us glimpse structures and regions of the cosmos that would otherwise be too faint or distant to see. You could think of them as the universe's foghorn lighthouses, briefly illuminating the darkest and most remote depths of space-time. However, these events are extraordinarily rare. In a typical galaxy like our Milky Way, a gamma-ray burst might occur only once every few million years, or even less frequently. Some astrophysicists estimate that one might happen in our galaxy roughly every 10 million years. They are so uncommon because they require very specific conditions: an extremely massive star, at least 20 or 30 times the mass of the Sun, collapsing in a particular way, or a direct collision between two incredibly dense, compact objects. So if we notice many gamma-ray bursts within a relatively short period of observational time, all coming from roughly the same region of the sky, that tells us something crucial. There must be many galaxies in that region, many sites where massive stars are exploding or compact objects are colliding. It is a telltale sign of an unusually high concentration of galaxies all clustered together. By analyzing the distribution of GRBs on the sky and measuring their redshifts to determine their distances, astronomers were able to map this colossal structure. They discovered a statistically significant excess of gamma-ray bursts in one particular patch of the sky, all at similar distances from us, around 10 billion light-years. This non-random clustering revealed the presence of the Hercules Corona Borealis Great Wall, a titanic slab of structure stitched into the early universe. Another gigantic and unusual structure in our universe, different in nature but equally impressive in size, is the Huge Large Quasar Group, or Huge LQG for short. This structure spans roughly 4 billion light-years in diameter, making it one of the largest known formations in the cosmos. For a single photon of light to travel from one side of this structure to the other would take almost as long as our planet has existed. Earth formed about 4.54 billion years ago, and light would need roughly 4 billion years to cross the huge LQG. We are dealing with timescales that simply escape our intuitive grasp, intervals so lengthy that entire species, ecosystems, and civilizations could rise and fall countless times over. If you could place the Huge Large Quasar Group on some massive cosmic scale and weigh it, an obviously impossible thought experiment, it would come out to be about 6.1 billion trillion times more massive than our Sun. Written in scientific notation, that is 6.1 times 10 to the 18th solar masses. To visualize this, imagine that every grain of sand on every beach on Earth represented the mass of one sun. You would need thousands of Earths covered in beaches to represent the total mass of this single structure. Scientists have found at least 73 identified quasars inside this immense formation, all relatively close to one another in cosmological terms. This suggests that they are gravitationally associated, or at least formed within the same large-scale cosmic environment. But what exactly are quasars? They are among the most fascinating topics in all of modern astrophysics. Quasars, short for quasi-stellar radio sources, are some of the most unusual, extreme, and energetic objects in the known universe. They are the blazing active cores of extremely distant galaxies, galaxies that existed when the universe was far younger than it is now. We observe these objects as they were billions of years ago because their light has been traveling through space all that time to reach our telescopes. At the heart of a quasar lies a truly gargantuan, supermassive black hole. We are not talking about ordinary black holes formed by the collapse of individual stars, which usually have masses between about 5 and 100 suns. The black holes that power quasars have millions or even billions of solar masses. They are gravitational monsters on a scale that is hard to wrap your mind around. This central black hole is actively devouring the surrounding matter at a furious, violent rate. Gas, dust, and occasionally whole stars are being pulled inward by its seemingly irresistible gravitational grip. But this matter does not fall straight in like water down a drain. Because of angular momentum, it forms a massive, swirling accretion disk around the black hole. The intense gravity twists and compresses the material in this accretion disk, heating it to absolutely extreme temperatures. We are talking about millions of degrees Celsius, far hotter than the core of most stars. At such hellish temperatures, the matter radiates energy across the entire electromagnetic spectrum: radio waves, microwaves, infrared light, visible light, ultraviolet, X-rays, and even gamma rays all pour out from the region around the black hole. This spinning accretion disk is literally the most luminous type of continuous radiation source known in the universe. The energy emitted by an active quasar is simply staggering. In many cases, a single quasar outshines not just its own host galaxy, but also countless others. Its radiative output can be tens, hundreds, or even thousands of times stronger than the combined light of all the stars in the Milky Way. Pause and think about that. Our galaxy contains between 200 and 400 billion stars, each a gigantic thermonuclear sphere pouring out energy every second. Add together the light from every one of those stars, and a single typical quasar can still be brighter. One object, technically a system of a black hole plus its accretion disk, can shine more intensely than hundreds of billions of stars put together. It is as if a single lighthouse were brighter than all the city lights on Earth combined. This incredible brightness has an important practical advantage for astronomers. Because quasars are so luminous, we can detect them at truly cosmological distances, distances so vast that we are seeing these objects as they were when the universe had lived only a small fraction of its current lifetime. That is why quasars are sometimes called beacons of the universe. They act like cosmic watchtowers that allow us to probe the distant, early universe. Scientists use quasars extensively to study the far-off cosmos and its motions, to map the distribution of matter on the largest scales, and even to investigate the nature of dark energy and the accelerated expansion of the universe. Quasars serve as brilliant reference points on the celestial sphere, helping us triangulate distances and decode the large-scale geometry and evolution of spacetime itself. One of the most distant quasars known, discovered relatively recently, lies about 13.1 billion light-years away from us. That colossal distance means that the light we are seeing now left that quasar 13.1 billion years ago, when the universe was only about 700 million years old. Given that the universe today is about 13.8 billion years old, we are observing this object as it appeared when the cosmos was a mere 5% of its present age. That makes it one of the oldest known objects in the observable universe, a genuine cosmic fossil that lets us peer back into an era when the universe was fundamentally different from how it is today. This quasar switched on around 690 million years after the Big Bang, during what cosmologists call the epoch of reionization, when the first generations of stars and galaxies were beginning to form and light up a cosmos that had previously been shrouded in darkness. This ancient quasar is also almost 3 times older than our entire solar system, which formed only about 4.6 billion years ago. When the light we now detect began its journey from that distant quasar, our sun did not exist. There was no Earth, no life, not even a nascent solar system. There was only a diffuse cloud of gas and dust somewhere in our galaxy that would, billions of years later, collapse into the star and planets we call home. Yet this ancient quasar still shines with incredible intensity, even after all that time and distance. Astronomers estimate that it radiates with a luminosity roughly 420 trillion times greater than that of our Sun. Written numerically, that is about 4.2 times 10 to the 14th times brighter than our star. It is a number so large that it almost ceases to have meaning in terms of everyday human experience. Scientists attribute this extreme luminosity to the presence, at the center of this quasar, of a truly monstrous supermassive black hole with about 1.6 billion times the mass of the Sun. This black hole is hundreds of times more massive than Sagittarius A star, the supermassive black hole at the heart of our own Milky Way, which only has about 4 million solar masses. The very existence of such an enormous black hole when the universe was just 700 million years old is itself a major puzzle. We do not yet fully understand how black holes could grow so big so quickly after the Big Bang. According to our current models of black hole growth, there simply should not have been enough time for a black hole to reach such a colossal mass. And yet it is there, stubbornly challenging our theories and hinting that there are still fundamental aspects of the early universe and the formation of cosmic structures that we do not completely understand. All of these gigantic structures we have discussed, the South Pole Wall, the Hercules Corona Borealis Great Wall, the huge large quasar group, are not merely astronomical curiosities or entries in some cosmic record book. They are the true building blocks of our universe on the very largest observable scales, the massive pieces which, assembled together, create the grand architecture of the cosmos. Seen together, they turn the night sky into a kind of blueprint, a map of how matter has flowed and clumped over billions of years to sculpt the universe we inhabit. Part 7. The Structure of the Observable Universe and the Journey Between Realities, the Final Limit. Look, do you see that almost invisible speck in the vastness of space? That tiny dot is our solar system. From this extreme cosmic vantage point, everything we know, the Earth, the Moon, Mars, Jupiter, Saturn, the Sun itself, shrinks to a minuscule, insignificant point in the fabric of the cosmos. All of human history, every war and every triumph, every scientific breakthrough and artistic masterpiece, everything has unfolded on that tiny pinprick of light that is barely distinguishable against the dark. Now pull back a little farther from that image. Increase the scale of your view. Here is where our parent star, the Sun, sits within the much larger context of the Milky Way galaxy. Our location is nothing special, nothing central. We live out in one of the minor spiral arms of the galaxy, about 26,000 light-years from the galactic center. From a certain perspective, we are galactic suburbanites, tucked away in the quiet outskirts far from the crowded, turbulent core, where stars are packed together far more densely. The Milky Way itself is a fairly typical barred spiral galaxy, with a diameter somewhere between 100,000 and 200,000 light-years, depending on how exactly you define its edge. It contains between 200 and 400 billion stars, although the precise number is impossible to determine. Some of those stars are far smaller and cooler than our Sun, faint red dwarfs that will burn dimly for trillions of years. Others are giant and supergiant stars, enormous blue-white furnaces that blaze furiously for just a few million years before detonating as spectacular supernovas. Pull back again. Widen your cosmic perspective once more. Now you can see the entire local group of galaxies. All of the bright points you see here are not individual stars. You are far too distant now for that, but whole galaxies, each containing its own hundreds of billions of stars, its own countless planetary systems, its own colorful nebulae, where new stars are being born. The local group is our immediate cosmic neighborhood. Here is the Andromeda Galaxy, officially catalogued as M31, the nearest large spiral galaxy to our own, and also the largest member of the local group. Andromeda is truly awe-inspiring. It holds roughly 1 trillion stars, more than twice as many as the Milky Way. If you could see Andromeda's full extent in Earth's night sky, instead of just the bright central core we currently glimpse, it would appear about 6 times larger than the full moon, covering a huge swath of the heavens from horizon to horizon. And here is the Triangulum Galaxy, also known as M33, the third largest galaxy in the local group. It is a beautiful, relatively modest spiral galaxy containing only around 40 billion stars. Alongside these 3 large spirals, the local group also contains dozens of smaller dwarf galaxies that orbit the bigger ones, like satellites circling planetary giants. Some of these dwarf galaxies are so faint and diffuse that they are extremely difficult to detect. The Canis Major dwarf galaxy, for example, is currently being torn apart and cannibalized by the Milky Way's gravitational pull. Its stars are being stripped away and assimilated into our galaxy in a slow but relentless process that will continue for hundreds of millions of years. The large and small Magellanic Clouds, irregular dwarf galaxies visible from Earth's southern hemisphere, are also doomed in the long run to merge with the Milky Way, their stars and gas woven into our own spiral structure. All of these galaxies are bound together gravitationally in a complex cosmic dance. They orbit one another, tug and pull on each other, and eventually, many of them will collide and merge into larger structures. The local group spans roughly 10 million light-years in diameter, a volume of space large enough to contain more than 80 known galaxies, and likely many more faint dwarf galaxies that we have not yet managed to discover. That span is about 100 times the width of our own galaxy. If the Milky Way were the size of a quarter resting in your palm, the entire local group would be about the size of a large dining table surrounding it. Now pull back yet again, stretching your perspective to even grander scales. Here we see the Virgo supercluster, also known as the local supercluster. This massive structure is about 20 times larger than the local group, stretching across roughly 110 million light-years. It contains around 100 groups and clusters of galaxies, the most prominent of which is the Virgo cluster that lends the entire supercluster its name. The Virgo cluster alone hosts at least 1,300 and possibly up to 2,000 individual galaxies. It is an enormous concentration of matter in the universe, and its combined gravity is so strong that it is pulling the entire local group, including the Milky Way, toward it. We are drifting in Virgo's direction at a speed of about 400 kilometers per second, though this motion is partially masked by the overall expansion of the universe. There are roughly 30,000 galaxies within the Virgo supercluster, each one a complete island universe in its own right, with its own stars, planets, nebulae, and perhaps its own forms of life. The total mass of this structure is around 10 to the 15th solar masses, a 1 followed by 15 zeros. It is a number so mind-bendingly large that any attempt to truly picture it quickly dissolves into abstraction. But your journey outward through the hierarchy of cosmic structures is not finished yet. Pull back again, widening your gaze to truly cosmic scales. Here we find Laniakea, its name in Hawaiian meaning immeasurable heaven or immense sky. This superstructure is about 3 times larger than the Virgo supercluster and stands as one of the biggest clearly defined structures we can currently map in the universe. Laniakea includes the Virgo supercluster we just examined, as well as the Hydra Centaurus supercluster, the Pavo Indus supercluster, and the region known as the Great Attractor, a mysterious area of space that appears to be drawing thousands of galaxies toward it with its enormous gravitational pull. The Great Attractor is partially hidden behind the plane of our own galaxy, making it difficult to observe directly, but its influence is unmistakable in the motions of nearby galaxies. This colossal structure contains roughly 100,000 galaxies, spread over some 520 million light-years. All of these galaxies are linked by large-scale gravitational flows, streaming like cosmic rivers toward regions of higher density. Laniakea is not simply a random grouping of galaxies. It is a dynamic system in which everything is moving together, influenced by gravity on truly grand scales. Yet even now, you are not done exploring the cosmic hierarchy. Pull back once more, pushing your perspective to the maximum. Here lies the Pisces-Cetus supercluster complex, also known as the Pisces-Cetus filament. This gigantic, massive galactic structure contains around 60 galaxy clusters, each cluster harboring hundreds or thousands of individual galaxies. The Pisces-Cetus supercluster complex stretches across roughly 1 billion light-years and holds more individual galaxies than there are grains of sand in all of Earth's deserts combined. If you tried to count each galaxy in this structure one by one at a rate of 1 galaxy per second without ever stopping to rest, it would take you thousands of years to finish. And every single one of those galaxies contains, on average, hundreds of billions of stars. This enormous complex is one of the filaments in the cosmic web, the frothy, large-scale structure that defines the distribution of matter in the universe. These filaments are like the strands of a 3-dimensional cosmic spider web, connecting huge nodes where multiple filaments intersect and where galaxy concentrations are densest. By now, you know what comes next in our journey. Pull back one final time, retreating to the widest vantage point possible. This is the entire observable universe, the totality of everything we can, even in principle, see or detect from our position in space and time. The view is at once beautiful, terrifying, and profoundly humbling. There are more than 2 trillion galaxies in the observable universe, according to the latest estimates, based on observations from the Hubble Space Telescope and other advanced instruments. Each one of those galaxies is a complete system comparable to the Milky Way. Some are smaller, containing only a few billion stars. Others are far larger, giant elliptical galaxies harboring several trillion suns. And the stars themselves, the total number of stars in the observable universe, truly defies comprehension. Estimates suggest there are about a septillion stars, 10 to the 24th of them. That is a 1 followed by 24 zeros. To put this in perspective, there are far more stars in the observable universe than grains of sand on all the beaches and in all the deserts on Earth combined, by a factor of perhaps hundreds or even thousands. The observable universe has its own rich, intricate structure on the largest scales. Galaxy clusters are not randomly sprinkled through space. They align into long, slender chains called filaments, and into enormous sheets or walls like the South Pole Wall and the Hercules Corona Borealis Great Wall that we have already discussed. These structures weave together into a vast three-dimensional network that permeates the entire observable cosmos, a colossal lacework of matter and light. Yet these bright threads of galaxies are separated by great domains of almost perfect emptiness. These regions are called cosmic voids. In these vast and shadowy expanses, there is virtually no visible matter at all. No galaxies, no stars, no planets, hardly any gas or dust. The density of matter inside these voids is extremely low, far below the cosmic average. In fact, a typical cubic meter inside a deep cosmic void contains fewer gas molecules than the best artificial vacuum we can create in a laboratory on Earth. It is a more perfect emptiness than anything our technology has ever achieved. These voids occupy most of the volume of the observable universe, perhaps 80% or more of all space. One of these voids has acquired a particularly mysterious and almost mythical reputation in modern cosmology: the Eridanus supervoid, also known as the cold spot. We have already encountered this strange region earlier in our journey, but it is worth revisiting it now in the context of the entire structure of the universe. This supervoid announced itself very early in cosmic history, only 380,000 years after the Big Bang. To place that in temporal context, the universe is now about 13.8 billion years old, so this void formed when the cosmos was a mere 0.003% of its current age. The universe was still a cosmic infant, glowing with leftover heat from the Big Bang, and the first large-scale structures were only beginning to form. The Eridanus supervoid is nearly 1 billion light-years across, a truly vast expanse of almost empty space. If it had the average matter density we would expect from our cosmological models, it could easily contain hundreds of thousands of galaxies with trillions of stars. Instead, it is conspicuously underpopulated, holding far fewer galaxies than it ought to. Some prominent scientists, including respected researchers in cosmology, believe that this enormous cold spot may be the aftermath of the greatest collision in known history, a direct interaction between different universes. It is an extraordinarily bold proposal, which, if correct, would utterly transform our understanding of reality itself. According to one modern cosmological idea, supported by certain inflationary models of the early universe, our observable universe is a kind of cosmic bubble. It is a huge, multi-dimensional sphere containing all the walls and chains of galaxies we have just toured, all the matter and energy we can detect, all the space-time we can possibly interact with. Now comes the truly mind-bending part of this theory. Imagine there are potentially an infinite number of such bubbles floating in a higher dimensional multiverse, or cosmic landscape. Each bubble is a separate universe with its own history, its own physical laws, possibly, and its own fundamental constants. Some bubbles may be similar to ours. Others could be radically different, with physics so alien that we could not survive there even for a microsecond. Billions of years ago, in the deep past of the cosmos, one of these neighboring universe bubbles drifted close to our own as both moved through the multiverse. Their walls eventually touched, creating a temporary bridge between two otherwise separate realities. It is like watching two water droplets on a surface glide toward each other until they finally merge into a single, larger droplet. But these universe bubbles did not remain merged. They kept moving, driven by the complex dynamics of the multiverse. The region where the bubbles had fused grew thinner and more strained, like two sticky surfaces slowly pulled apart after having briefly adhered. The tension increased until at last the connection snapped violently, and the two bubbles separated again, returning to being independent entities. At this critical moment of separation, the second universe physically tore away some of the material from our cosmic bubble. All those galaxies, all that dark matter, all the energy that once filled the region that would become the Eridanus supervoid were literally ripped out of our universe and dragged into the neighboring universe as it retreated. What remained behind was a massive void, a permanent cosmic scar, marking the place where our universe was wounded by contact with another reality. This theory would neatly explain why the Eridanus supervoid is abnormally large and cold, why it contains far less matter than standard cosmological models predict. It turns this region into physical evidence of an event of almost unimaginable significance: the collision of two universes. If this bubble universe picture is correct, then in principle, we might be able to travel between bubbles, visiting parallel or alternate universes. But there is a colossal practical problem. Flying to the supposed wall of our universe, to that boundary where a connection to another cosmos might exist, would take effectively forever. Even at the speed of light, we would arrive long after our sun had died. And then it would take an even more unimaginable span of time to traverse the inter-universal space, the gulf between cosmic bubbles, to reach another universe. The distances are so enormous that even with hypothetical technology capable of faster-than-light travel, the journey might still consume billions of years. So we are forced to think about shortcuts, cosmic portals, or wormholes. In theory, it would work like this. Picture a flat sheet of paper with point A marked on one end and point B marked on the opposite end. Usually, to travel from A to B, you must move along the entire surface of the paper, following the long route from one side to the other. That is how ordinary space travel works in our familiar 3 dimensions. But instead of trudging along the full length of the sheet, imagine folding the paper so that point A lies directly above point B, nearly touching. Now the 2 points are separated, not by the whole length of the page, but by a tiny fraction of a millimeter. All that remains is to punch a small hole through both points simultaneously, creating a direct tunnel from A to B. This hole through the folded paper is analogous to a wormhole in real space-time. Instead of plodding through billions of light-years of normal space, you simply enter one mouth of the wormhole and exit through the other. The journey could take only seconds or minutes, regardless of how far apart the 2 points are in ordinary space. Some prominent scientists and theoretical physicists, including figures such as Nobel Prize winner Kip Thorne, believe that such shortcuts through space-time and between universes might be hidden inside certain types of black holes. Not every black hole would contain a traversable wormhole. Many would just lead straight to destructive singularities where you would be annihilated instantly. But under the right conditions, with exactly the right physics, a specific black hole might harbor a stable tunnel. As we noted earlier, the question then becomes, how do you survive falling into a black hole to make use of such a portal? The answer lies in careful selection. You must choose a black hole large enough, a supermassive black hole like those found at the centers of galaxies. These gravitational monsters can be millions or billions of times more massive than the Sun, and their event horizons are correspondingly vast, stretching across millions or even billions of kilometers. Because of this enormous size, the gravitational gradient at the event horizon is relatively gentle. The gravitational pull increases gradually rather than abruptly. This means that the gravitational force on your head and on your feet would be nearly the same at the moment you cross the event horizon. You would not experience the violent tidal forces, spaghettification, that would tear you apart in a smaller black hole. You could cross the horizon relatively intact and even feel reasonably comfortable, at least for a while. Who knows, perhaps if you survived a carefully controlled plunge into such a massive black hole, and if you navigated successfully through the extreme environment inside the horizon, you would eventually find yourself emerging into a universe utterly different from our own. A place where different physical laws hold sway, where the fundamental constants take on new values, where the number of spatial dimensions might be different, where chemistry and biology operate according to alien principles. You might burst out of a corresponding white hole in that other universe, being hurled into an alien cosmos full of wonders and phenomena beyond human imagination. Galaxies with impossible shapes, stars shining in colors that do not exist in our electromagnetic spectrum, life forms built on principles entirely unlike the carbon-based biochemistry we know. For now, of course, all of this remains safely within the realm of speculative theory, advanced physics, and elegant mathematics. It is serious science, grounded in rigorous equations and fundamental principles, but it has not yet, and perhaps may never, be tested directly by experiment. No one has ever fallen into a black hole and survived to report back. No one has passed through a wormhole. No one has stepped into another universe. Yet, the mere fact that the mathematics of general relativity permits such possibilities is deeply meaningful. In physics, what is mathematically allowed often turns out to exist somewhere in nature. Black holes were predicted mathematically decades before we found convincing observational evidence for them. Gravitational waves were predicted by Einstein in 1916 and were not detected directly until 2015, nearly a century later. So who can say? Perhaps in some distant future, when humanity has developed technologies we can barely imagine today, when we have learned to manipulate space-time itself, we will use wormholes to travel between universes. We may explore the multiverse, visiting alternative realities where history took different turns, where the laws of physics permit phenomena impossible in our cosmos. For now, all we can do is turn our telescopes toward the stars, measure the redshifts of distant galaxies, study the cosmic microwave background for subtle anomalies, and build ever more sophisticated mathematical models of the cosmos. Each observation, each measurement, each new theory brings us a little closer to understanding the true nature of reality. And in the meantime, we continue our voyage through space and time, explorers in an immense and incomprehensibly beautiful universe, searching for answers to the deepest questions humanity has ever asked. Where did we come from? Where are we going? Are we alone? What lies beyond the limits of our observable universe? Do other universes exist? And if they do, will we ever walk beneath their alien skies? The cosmos guards its secrets jealously, but slowly, patiently, with ingenuity and an insatiable curiosity, we are beginning to pry them open. The journey has only just begun.